Hi friends, in this video we will discuss about Dirichlet conditions. Actually, Fourier said that any signal can be expressed as a linear combination of complex exponential. However, he has not carried out the mathematical analysis for that. It is P.L. Dirichlet who has conducted the mathematical analysis and came with some conditions for the existence of Fourier series. So Dirichlet was a famous German mathematician, and he is famous for his contributions in Fourier series analysis. In 1989, he proposed the precise conditions under which the Fourier series exists for a periodic signal. So if the signal satisfies these conditions, then we can say that the Fourier series exists for that particular signal. For x of t equals its Fourier series representation, there are some conditions developed by Dirichlet, and these conditions are known as Dirichlet conditions. So Dirichlet shows that if x of t satisfied these conditions, its Fourier series is guaranteed to converge point-wise at all points where x of t is continuous. That is Dirichlet's main contribution. He has done this in 1829 after the death of Fourier. So now let us analyze the conditions one by one, and let us check whether there are some signal which does not obey this Dirichlet condition, so that there is no Fourier series exists for those signals. This is the first Dirichlet condition, that is Dirichlet condition 1. Over any period, x of t must be absolutely integrable. That is, the given signal x of t must be absolutely integrable over any period. So that is the first condition, Dirichlet condition. So that mathematically we can represent integral over a period x of t. So that is the magnitude of x of t dt must be less than infinity. So that means the signal x of t is absolutely integral. In that case, we know that the expression for ak, the Fourier series coefficient, is given by 1 by t integral over a period t x of t e power j minus jk omega 0 t dt. So we know that the magnitude of e power jk omega 0 t is 1. So we can write this equation as 1 by t integral over a period t x of t, that is magnitude of x of t dt. So this equation says that if integral x of t is dt is less than infinity, that is it is absolutely integrable, then ak, the Fourier series coefficients, are also less than infinity. That is, we can absolutely integrate this signal x of t. So that is the first Dirichlet condition. So the first Dirichlet condition says that over any period x of t must be absolutely integral. So now the question is there any signal that violates Dirichlet's condition? Here I have shown a signal, and the equation for the signal is given by x of t is equal to 1 by t for t less than or equal to that is in the period 0 to 1. The equation of the signal is 1 by t. You can see that when the signal is approaching 0, its value is going to infinity. So in every period its value is going to infinity. This signal is not absolutely integrable. So x of t is equal to 1 by t. This signal is an example of the signal which violates the Dirichlet condition 1. So the second condition of Dirichlet conditions is this: in any finite interval of time, x of t must have only a finite number of maxima and minima for a single period. That is the second condition in the Dirichlet condition. Or in other words, we can say that in any interval of time, x of t must be a bounded variation. X of t must be a bounded variation. So that is the second Dirichlet condition. That is, at any interval of time, x of t must have only finite number of maxima and minima for a single period. So now there is a question: is there any signal that violates Dirichlet condition 2? Here I have shown a signal which violates the Dirichlet condition 2. So the equation for the signal is given as x of t is equal to sine 2 pi by t. So sine 2 pi by t over a period 0 to 1. So this signal is an example of the signal which violates the Dirichlet condition 2. So we can see that this signal obeys the first condition, that is it's absolutely integrable, but it violates that there are infinite number of maxima and minima. So if you plot this signal, you can see that when it is approaching the 0, here you can see that its frequency is increasing. So you can see that there will be infinite number of maximas and minimas. There will be infinite number of maximas and minimas for this signal. So if this kind of signals are there, then it will not have a valid Fourier series. So this signal violates the Dirichlet condition 2. So now we will analyze the Dirichlet condition 3. So Dirichlet condition 3 says that in any finite interval of time, there must be only a finite number of discontinuities. So this term is very important. There must be only finite number of discontinuities, and each of these discontinuities are also finite. So this is the third condition, Dirichlet condition. So third Dirichlet condition says that in any finite interval of time, there must be only a finite number of discontinuities in the signal, and each of these discontinuities are also finite. So for a periodic signal with a finite number of discontinuities in each period, the Fourier series representation is equal to the signal, that is there exists a Fourier series. So except at the isolated points of discontinuity, except at the point of discontinuity, we have a valid Fourier series for that particular signal. So now the question is, what happens at the period of discontinuity, at the points of discontinuity? So at this points of discontinuity, the series converges to the average value of the signal on both the sides of the discontinuity. For example, if there is a discontinuity at particular point, the Fourier series will converge with the average value on both the sides of the discontinuity. So now the question is there any signal that violates Dirichlet condition 3? So here I have shown a signal which violates the Dirichlet condition 3. The speciality of the signal is that when half of the distance is moved, the value of the signal will be reduced by half. So again, when it moves to the other half, again the value of the signal will be reduced to half. So this will be continued. So I have put 3 dots here. So when it reaches from 0 to 8, there will be an infinite number of discontinuities like this. So this is a never ending signal. So its value will be going like this. This is a never ending signal, and we can see that there are infinite number of discontinuities in this signal. Particular signal violates the Dirichlet condition 3. That is, Dirichlet condition 3 says that there should be only a finite number of discontinuities in one period, but this signal is having an infinite number of discontinuities. So from the signals I have shown as examples, we can conclude that the signals that do not satisfy the Dirichlet conditions are very rare, and these signals are pathological in nature. So we do not expect these kind of signals in the practical situations. Hence we can say that the Fourier series representation can be applied to a large class of practical signals. There are exceptions like this which do not obey the Dirichlet conditions, but for a large class of the signals, practical signals, this Fourier series exists. That is, this obeys the Dirichlet conditions. So that is why the reason Fourier series analysis is very famous in signals and system domain. So I will conclude the Dirichlet condition. So the first condition is saying about the signal must be absolutely integrable. So the second condition says that there should be a finite number of minima and maxima. And the third condition says that there should be a finite number of discontinuities. So if our signal obeys the Dirichlet conditions 1, 2 and 3, so if our signal obeys Dirichlet condition, we can say that there is a valid Fourier series exists for that particular signal. Thank you for watching.